Here, and special thank you to Dr. Surya Rao for agreeing to host me, and Dr. Sandeep Narayan City for being the sort of medium and handling the logistics and everything. I'm really glad to be here. As Dr. Narayan City mentioned, I am working with Professor Amit Tandon on sort of physical processes that affect oxygen transport in the ET2, but the first chapter kind of grew out from looking at eddy transport into like a global look at how eddies affect tracer transport across the global ocean. And just to start off with, I would like to thank the Office of Naval Research, which funded all of the research that went into this. And I would like to point out like a few other collaborators. I wouldn't say collaborators, but most of the people that we've had discussions with that sort of helped develop the latter half of this project, which are Dr. Sylvia Cole at Woods Hole, Dr. Eric DeSaro, who some of you might know from IPL, University of Washington, and Dr. Simran Wortham at the Northwest Research Associates. And just to start off with, I would really, this is a figure that I really like. This on the left is a map of the Gulf Stream as was made by Benjamin Franklin in 1776. And this on the right is like a NASA visualization of what the Gulf Stream streamlines look like now. And while, of course, the level of detail and all of the associated sort of advancements in science and modeling that have come with the last 150 years sort of make these figures very contrasting. One of the major ways in which our understanding of the ocean has changed is highlighted really well in these really large circular walls that sort of pinch off from the Gulf Stream. And these large-scale structures called mesoscale eddies are going to be the focus of my talk today. I will begin with an introduction to eddies in general. What are they? What do they do to tracers in the ocean? Just like one slide on what exactly I mean when I talk about tracers, and the two mechanisms by which we think eddies affect tracers, which are stirring and coherent advection. I will have a brief segue into how these effects are parameterized, starting off with why parameterizations are necessary in the first place, and end that section with what are the existing gaps in our current parameterization and what this current study hopes to address. Then we will begin with eddy diffusivities, which relate to the eddy diffusivities that I'll talk about in the parameterization sort of section. And then finally, I'll talk about stirring and coherent advective transport, ending with a note on how exactly our work can inform parameterizations. And one of the sort of really important reasons why we care about eddies is, number one, as I mentioned, they affect tracers quite drastically. But also because if you look at this map, which was published very recently by Cortez Morales in 2026, you see blue versus red regions of the ocean, which highlight where exactly in the ocean is the eddy kinetic energy, sort of the dynamic variable part of the kinetic energy budget of the ocean is dominant, which is majority of the ocean in blue, and where the mean flow, the red is more dominant. So by and large, our understanding of the dynamical circulation of the Earth really depends on understanding how eddies interact with the mean flow and how eddies interact with each other. And because I really like giving away spoilers at the beginning of my presentation, I will say that I have absolutely no idea how my work will inform parameterizations, but that is one of the ways in which future researchers can take this up or collaborate and so on. All right, so what are mesoscale eddies? This is a sort of video, if it plays, yeah, there we go. On from May of this year to approximately July of this year on the surface sea level anomaly over the Eastern Pacific and the Atlantic. And one of the most dominant features that jumps out whenever you look at these maps are these really large circular features. Blues are anticyclonic depressions, and red are cyclonic sort of lifted up of the sea surface. And these are what we typically call mesoscale eddies. These are energetic swirling features. They're present throughout the global ocean, and they're very visible through satellite altimetry, which is one of the ways that our understanding of the ocean has drastically increased in the last few decades. The idea with satellite altimetry is that, of course, you can correlate the variations in the height of the sea surface to variations in the pressure below the sea surface, and this gives you an indicator of what the velocities of the ocean are with an approximate geostrophic balance. These eddies, if you sort of look at them very closely over an extended period of time, will appear to drift westwards as they evolve, and this is because they're so large that they can experience the difference in the Earth's rotational frequency as they go over their sort of meridional extent from south to north. And because of that and the ways in which the Coriolis term interacts with the interacts in the Navier-Stokes momentum equations, they tend to these eddies can be barotropic or baroclinic. When I say barotropic, I mean that they have a uniform depth extent, or baroclinic, by which they have like a sort of non-uniform depth extent. They have like a decay with depth typically. And the formation mechanism of these eddies can be varied depending on, of course, if they're baroclinic or barotropic, but they're typically linked to one of these 6 terms in the vorticity evolution equation, where zeta is the vertical relative vorticity, essentially dou x to v minus dou u, dou I u. The first term is just like a mean advective term. The second is the baroclinic term, which is related to the difference in the pressure and the density surfaces of the ocean. The third and the sixth term are the stress terms. So you can have vorticity change via vertical or horizontal stresses on the ocean. Wind stress plays a key role in this one. The fourth term is just an evolution of the beta effect. Essentially, if you drift northwards, you're going to reduce your you're going to increase your background F, which means that you're going to reduce your beta just because you conserve absolute vorticity. And the fifth term is what we typically call the vortex stretching term. If the flow is flowing over some sort of topography, the vorticity of the water column changes as a result of the essentially the compression of the water column. So that's an introduction to eddies, and just because I really just on this very complete side note. This really large red spot over the Eastern Pacific is one of the indicators of climate phenomena that we're going through right now, which is the sort of super El Nino. And the idea behind this large positive sea level anomaly is that the easterly winds that are typically forcing this water westwards are not strong right now. So the water kind of sloshes back and creates this really large positive sea level anomaly. It is quite remarkable that you can see this by osmometry. Tracers, typically when you hear the word tracer, you're thinking of a dye, and that is something that you put in water that tracks the flow field of the water that can look something like this. In the Chicago River, they pour green dye into the river to sort of celebrate St. Patrick's Day. But in the oceanographic context, a tracer is really any fluid property that you can use to track the flow. It typically can be salinity or temperature. If you're looking at the physical variables, it can be oxygen, nitrate, phosphate, other biogeochemical tracers as well. In this sort of presentation, I'm going to be focusing on salinity and salt and heat really as tracers, but you can typically use the concepts that I am talking about in the next few slides on any tracer of your choosing. And how exactly do these concepts relate to each other? How do these affect tracers? Well, one of the most dominant start ways that they affect tracers is by stirring. Similar to how you pour coffee into water or milk and then stir it using a spoon, eddies essentially do the exact same thing by stirring water masses around their edges. This is a false color image of, pretty sure this is chlorophyll, but could be really any tracer again. And you can see that the eddies are essentially filamenting and stirring one water mass with the other. One sort of caveat that I'll add is that stirring is not mixing. This is something that I essentially learned through being chastised quite a bit by my advisor. But the idea of it stirring is that it is reversible. So if you were in a hypothetical world to completely reverse the flow of time, essentially undo the effect of these eddies, these water masses would go back to how they were before. So stirring is a reversible process, but the idea behind stirring is that essentially what it is doing is it's enhancing gradients of these tracer properties at a very small distance. So if the mean background gradient was much larger at first, stirring quite enhances that gradient, and that allows smaller scale processes like turbulent mixing or essentially molecular mixing to take over. So the idea of stirring is that it aids in mixing, but it is not stirring, and it is not mixing, and that's a very important distinction. We typically model stirring effects of eddies as a diffusive process. The idea behind that being that if you were to take a snapshot of the flow field and inject particles in that flow field, according to what these eddies are doing, you would not observe a diffusive effect as such, but if you were to take a slightly displaced particle and then advect it as well, and take multiple snapshots of this, this would look like a diffusive process. So that's why you model eddies or eddy stirring as a typically as a diffusive. Another way in which eddies can affect tracers is something that I like to call coherent advection. And the idea behind this is simple. Let's say I was to take a balloon and flip it air from where I came from in New Bedford. And then I carried that balloon with me on the plane, brought it over to IIT in Pune in the seminar hall, and then popped it essentially over here. By doing so, I have essentially transported air masses and water masses in the case of eddies all the way from the US to this location in Pune, and I've changed the properties of the air at this location via this transport. And this happens in the ocean as well. This is a sort of recent development in the field. Sort of started by George Haller's paper on Lagrangian structures in 2014. But this figure is taken from Liu and Abernathy in 2023, and you can see that as the eddy advects, drifts westward, a large portion of the water mass inside that eddy is coherently transported along with the eddy. And really, this sort of phenomenon is limited to the core of the eddy, so the core is much more coherent than the edges. But this is the central idea behind coherent advection. And the reason why this happens is because eddies are not just most eddies are not just Rossby wave perturbations in the flow field. The idea being that they're not just linear features that you can approximate with a geostructural balance and then be done with it. They are nonlinear, and the nonlinear term in the momentum equation plays a role in the dynamics of these eddies. And that leads to this sort of coherent core, which acts as a transport barrier. So fluid cannot go out of the core, fluid cannot come into the core, and that prevents mixing of and homogenization of the eddy. This has been known in literature for quite a while. These were simulations of the sort of vortex cores and Lagrangian particles done by Provenzale in 1999. Essentially, what they did was that they seeded the background with all these black dots, which are Lagrangian particles. And as they advected them, the background particles stayed in the background, whereas the particles that were kept inside of a single vortex core completely stayed within that vortex. The vortex remained coherent for the duration of this simulation. And this was a much more idealized simulation. Sort of more realistic simulations were done by Jeff Early in 2011, which showed the exact same phenomena that these eddies can act as material transport, can carry out material transport from their origin to where they dissipate. And now that I've talked about the process by which these eddies affect parameterization, the effect tracers, why do we need parameterizations to model these effects? Well, the primary reason is that if you contrast the model on the left to the model on the right, the model on the left has much higher resolution, the model on the right is much coarser. And well, it's not just limited to mesoscale eddies, like our mesoscale level phenomena. Numerical models rely on a discretized grid that can be in time or that can be in space or time for that can be in time or space, which is typically most finite volume models. But it can also be in wave number and frequency space, which are the Fourier transforms for this. So if you're running a spectral model, you'll be discretizing in wave number and frequency. And what that does is it essentially imposes length and time scales of accuracy on your model. Your model is only as accurate as the smallest length scale that it resolves. What that means is that you're averaging across scales this sort of this parameter, or changing this parameter, can lead to drastically different results in what your model tells you. For instance, in 2014, Pradal and Nanobasican showed how you can change the ready diffusivity number from approximately 400 to 2400. And what exactly does that do to your sea surface temperature on the left and the surface temperature on the right? And you can see that there's a really large range of uncertainties. You can go from local cooling in the North Pacific to local heating of an order of approximately 12 degrees Celsius over a 500-year span. So constraining what the value of this ready diffusivity is pretty important for essentially future projections and making sure your models are doing what they're supposed to. And again, this sort of variation is really bad because this leads to uncertainties, and policymakers who are not well versed in science may not understand where these uncertainties are coming from. And thus it is important for us as scientists to really constrain these and communicate the uncertainties of our results to the broader public better. Another way by which you have to, another reason why you have to sort of parameterize the effects of eddies is that just because you have parameterized this diffusivity in the previous slide, as I talked about, your problem is not quite solved. If you are only diffusing along, if you're only diffusing tracers along isopycnals, you are not going to affect the mean density of the ocean at all, which means that there is no balance between your mean advection and your eddy transport. And this was identified as early as the 90s by Gent and McWilliams, who observed that in a model run that they were running, you had a large amount of convective adjustment happening at the mostly in the Southern Ocean, because it's a very mesoscale energetic region of the ocean. And all of these contours really represent areas in which denser fluid happens to fall over lighter fluid in your models, which means that there has to be some sort of convective adjustment to account for that. And then when they sort of implemented this parameterization, which I'll talk about just now, that amount of convective adjustment drastically reduced, which means that your model was being much more physical in dealing with these. What eddies typically do to isopycnals and to isopycnal thickness levels is that they're going to diffuse the thickness. The idea being that if you have a thicker isopycnal over, or if you have a thicker density surface over here and a sort of smaller one over here, the effective eddies will be to diffuse this thickness to uniformize all these density surfaces. And this sort of parametric form of the Gent-McWilliams skew flux was devised back in the 90s by Peter Chen and Jim. Okay, so now you have these two modern parameterizations which are used in all ocean models nowadays. What are the gaps in this formulation? Well, both of these parameterizations, both the ready as well as the Gent-McWilliams, you can see that there's a local kappa associated with the Gent-McWilliams as well. All these parameterizations model eddy transport as local down gradient diffusion. But we know that eddies are nonlinear, which means that the nonlinear term, the u dot grad u term in your momentum equation plays a role, and that eddies can trap and coherently advect these water masses inside them. So and these effects are inherently non-local. Like if you're trapping water mass at this point and then advecting it all the way to this, you cannot model this as a local process in your model that is not resolving eddies at all. So how do you parameterize some of this? And if you don't parameterize it, how much does this effect matter? This is something that we have tried to answer for salt and heat in this study. How much does that matter for density? And how much do you need to change the Gent-McWilliams parameterization to account for this? I have no idea. What exactly is the true value of the ready diffusivity coefficient across the ocean, which is something that I said we need to constrain our models, and we have attempted to do that in this work. And how does this tracer diffusivity kappa rho, the ready diffusivity coefficient, relate to the Gent-McWilliams diffusivity that you saw on the previous slide? And Nick Kuster, Dhruv Bawala, and Stuart Groskamp have a nice paper on how exactly these two concepts relate to each other. Okay. So I'll start with the first question, which is how exactly do you characterize ready diffusivity, and how exactly we have attempted to do that in this study. In 2015, Sylvia Cole at Woods Hole did this by looking at essentially what the fluctuations in salinity or temperature, you can choose either one, because on an isopycnol, the salinity variance will be related to the temperature variance. And how exactly do these variances relate to the mean gradient? And with this sort of idea, you can create mixing length, where a mixing length is essentially a generalization of Prandtl's idea of turbulent mixing. If you are taking a water mass, or if you're stirring a water mass from this end to this end, by identifying how much the properties of this water mass differ from the local water mass, you can get an idea of how far it has traveled by relating it to the mean background gradient. So you can get a mixing length from relating these anomalies to the gradient, and then you can multiply that with a velocity estimate, a URMS value associated with these eddies to get a diffusivity value, where the URMS is typically diagnosed using a model. What we do in this work is that we take Argo profile data from Simu Sousa et al. Yuri was a former PhD student of Professor Tanis. And what he did was that he compiled a data set containing all the Argo profiles in the ocean with data about mesoscale eddies from this eddy atlas. So you can co-locate profiles within eddies and then see what exactly the properties of water masses inside and outside eddies are. And just as a schematic of how exactly an Argo float works, these are sort of autonomous floats that are typically free floating at the surface in the beginning to communicate with iridium satellites. They drift down to 1,000 meters, sampling the water column all across. They drift at 1,000 meters for a bit, go all the way down to 2,000 for the current generation of Argo floats. So you're essentially getting a whole sample of the water column every few days or so. I think it's 5 days or something. And these have to really revolutionize our understanding of the ocean. You now do not have to go all the way to the Southern Ocean to get an idea of what the ACC is doing. You can just deploy a bunch of floats and then get real-time data at a very high temporal frequency. And this is sort of the schematic for what the eddy atlas tells you. It tells you all about the properties of the eddies, what the contour is, where the eddy is translating, and so on and so forth. And this is what we essentially are going to use in our analysis. Okay, so you have this sort of key set of equations that you're going to use to characterize kappa H. How do you define this S prime or theta prime, which is essentially the salinity or temperature anomaly associated with stirring? Well, you're going to measure what the properties of the salinity and the temperature properties of the water column are, and then you're going to essentially say how much are they deviating from what the mean is, or from what the rest of the or what the water column should be doing essentially. And to define what the water column should be doing, we use something called a quantitology. This is the Remick-Gilson Argo quantitology, where you're essentially averaging across multiple Argo profiles in a region to see what the mean state of the water column in that region should be. So essentially what you're doing is essentially subtracting what the measured profile is S from the mean profile to get what the anomaly is. And one of the questions you can ask with this method is, are all anomalies attributable to stirring effects? Well, the answer is clearly no, because near the surface, your anomalies are typically profiles are going to be affected by surface effects more likely than not. And so in our analysis, we remove the mixed layer entirely. This is a variation of the mixed layer in the Eastern Pacific. So you're going to remove the top 10 meters or top 80 meters, depending on what your mixed layer is doing at that profile, from your analysis altogether. And we do this using an Argo climatology created by Polkett, Talley, Dixon, and Bernick. And another question at this point, once you remove the mixed layer, is what exactly is a stirring anomaly, and how much of your anomaly is coming from the stirring effects of eddies? So Sylvia Cole in 2015 sort of did all of this analysis via, let's say if you have an Argo profile marked by this blue star over here at this location in the Eastern Equatorial Pacific. What you're going to do is you're going to interpolate the climatology to that cast location and then average in a 1-year window around the time of the cast. What that looks like in effect is something like this. So if your Argo profile is measuring salinity profile marked in blue, you're going to average the climatology in a 1-year window, which are these gray lines, to get this red line, which is essentially your mean profile. And the deviations from the blue line to the red line are your salinity anomalies. But one of the questions that we were sort of asking is that this particular profile was taken inside of a mesoscale eddy. It was first detected at this location and then drifted westward. So how much of this difference is due to stirring versus coherent advection, as we talked about earlier? And how exactly do you separate that? Our approach that we took in this study was quite conservative. What we do is that essentially we're going to be interpolating the climatology to the detected locations of the eddy instead of the detected location of the cast. What that looks like is that the cast is marked in blue, and you're going to interpolate climatology to each of these green dots, which is one of these gray lines. And then essentially you combine all of these gray lines into one representative profile, which is the red line, by minimizing the difference of what you observe from what you should be observing. And that gives you your new sort of climatology, new profile that you get your new anomalies from. So our anomalies are marked in green, whereas Sylvia's anomalies are marked in red. And you can see that there's a reduction because we are trying to account for the trapping and coherent advection that I talked about earlier. So effectively what we are trying to give you is essentially a lower bound on what anomalies you can attribute to this mixing and stirring effect. And it is these anomalies that should be used in your mixing length analysis to give you diffusivities, is what we are planning. Okay, so if you do that, what does your diffusivity map look like? For an isopycnal level of 27 kilograms per meter cube, if you were to plot kappa rho across the global ocean, that map looks something like this for our analysis. But as for Sylvia's analysis, these values will be larger. And the ratio of our numbers to Sylvia's is given in this sort of inset plot over here. On the face of it, these numbers look good. They are of the right order, and they typically match the patterns that you would expect to be observing. You have elevated diffusivities near the Gulf Stream, which is really energetic in the mesoscale, the Kuroshio and the ACC as well, although you're kind of missing out on a lot of the ACC because you don't have enough Argo profiles inside eddies. And just as a sort of detour that I don't usually do, but you have elevated diffusivities across the western Bay of Bengal as well, because of the eastern boundary current that flows along here. And this was something that Professor Tandon was quite interested in, and we talked more about in a smaller seminar. Anyways, if you look at these ratios, you observe really almost an order of magnitude lower ratios at this location of the ocean, which is the southern Indian Ocean just off of the coast of Western Australia, as well as in the South Atlantic subtropical gyre and the North Atlantic subtropical gyre. And there are very interesting dynamical regions why you observe much lower values over here compared to Sylvia's than the rest of the ocean. And we'll get to that when I talk about coherent advection. But first, just to look at whether these numbers make sense in relation to observations, we compared our numbers to what you observed from in situ observations during the NOT-TRE field campaign. This was the North Atlantic Trace and Release experiment done in the, I want to say the 80s, but don't quote me on that. And there were a bunch of sort of dye release experiments done in this part of the ocean, and then they looked at where the dye flowed to characterize the diffusivity of the along isopycnal as well as diapycnal diffusivity of the water column over there. And if you compare our numbers, which are in blue, to observational estimates from the NOT-TRE field campaign, which are these dots at different depth levels, you can see that our estimates match quite well, well within the bounds of error. What our estimates also do is match the sort of semi-empirical theoretical estimates of Groskamp, who used this thing called the mean flow suppression theory to devise diffusivities. And both of our numbers are much lower than Sylvia's, because Sylvia's beating was sort of mixing the variance due to two processes into her analysis. So how do these numbers compare? Pretty well. And we could have stopped here and essentially published this work as a diffusivity work, and we would have been happy. But we wanted to look at this further because of the aforementioned discussions that we had with other scientists as well. So now we can make estimates of diffusive transport because we have diffusivities across the ocean. But we discarded the coherent advective piece altogether when we came up with this. So what about that? How much does that matter? And to characterize how much this coherent advection matters, you cannot use an Eulerian eddy map because an Eulerian eddy, because Eulerian maps do not give you how coherent the eddy is. So instead of that, we use this global Lagrangian eddy data set, which is compiled by Lou and Abernathy in 2023. The idea being that they observed geostrophic velocities from satellite altimetry over a 20-year time span. They seeded their model with these, they initialized their model with these geostrophic velocities and then seeded their models with millions of Lagrangian particles at each time step, and then advected the particles according to the flow fields prescribed. And then essentially what they did was they looked at how these particles were sort of clustering and how many of these particles were staying together coherently inside eddies, and those define what your rotationally coherent Lagrangian vortices or RCLVs are. And the generation of these RCLVs is much more different than what you would typically observe to satellite altimetry. Through SSH, through satellites, you typically see that there's a lot of eddies near the Gulf Stream, the Kuroshio, and the ACC. But these rotationally coherent vortices typically tend to occur along the South Atlantic subtropical gyres, the Southern Indian Ocean off of the western coast of Australia. And these are important because these are the regions where we thought we observed lower diffusivities as well. And this is just a figure from their paper talking about like a single instance of this quantity that they use to characterize these vortices and how they propagate. And to use this data set, essentially we're going to go back to the tracer evolution equation that looks something like this. The tracer tendency relates to the advective tendency, to the diffusive tendency, and to sources and sinks of tracers. The diffusive transport is easy. We already have maps of kappa H. We already have what the gradients of these tracers are from climatology, so you can compute this. This is easy to do for mean flow, but it is really hard to do because coherent advective transport via eddies is some nonlinear part of this term, but it is really hard to resolve the gradients of velocities and tracers inside and outside eddies. So parameterizing this is really hard within this term. Which means that you're essentially forced to consider your transport as a source or a sink term. The idea being that if you have a Lagrangian eddy that formed over here and then advected westward, you're going to essentially transport water at this location marked by the red circle to the location marked by the green circle. And for salinity, the profiles at the start location and the end location look something like this. For temperature, they look something like this. And for density, they look. What we do is that we take assumptions about the depth of the eddy. For our main text, we use a depth of 500 meters across the global ocean, and then essentially integrate from the surface to this depth and try to find how much tracer is carried along by this eddy to the final location. And the difference of the tracer content of the final location to the initial location gives you how much your tracer tendency should change. We also do this analysis for 1,000 meters, but that's a supplementary figure I'm not showing here. Okay, final few slides. And getting to the meat of the matter, really, how much do eddies move stuff around? For diffusive fluxes, what we're going to show here is diffusive deposition, which means we're going to show how much the diffusive processes affect tracer tendencies at a given grid location. So that's a divergence of the diffusive flux. And the patterns look very similar to what you would expect. The energetically mesoscale areas like the Gulf Stream, the Kuroshio, and the ACC are highlighted because these are areas that enhance both diffusivities as well as gradients. But the coherent advective deposition looks vastly different. All of this is for salt, and I'm going to show heat in a minute. For coherent advection, it is really where these Lagrangian eddies are forming and dissipating that matters. So you see enhanced freshening of the North Atlantic because you are advecting eddies that form near the eastern boundary currents over here, and then they drift westward and deposit the water over here. At depth, the eastern North Atlantic is fresher than the western North Atlantic, so you observe a freshening effect. You can create similar conclusions for this freshening of the southern Indian Ocean that you see. The ACC is much fresher compared to the background waters of the southern Indian Ocean. So when you have these rotation vortices that form over here and then drift westward and equatorward, you observe a freshening effect due to that phenomenon. And all across the northern equatorial Pacific, you observe a freshening because the equatorial current creates these pinch-off rings that drift westward and then deposit fresher water from the equatorial current into the subtropical Pacific. The subtropical, South Atlantic subtropical gyre is also sort of highlighted in this, but it shows up more so in heat. And the maps look very similar to what they look like for salt. And the reasons for most of these patterns are similar to what I described earlier. And one final point that I will drive home is that this sort of coherent advective term at individual grid locations is of the same order of magnitude as what you would get from diffusive deposition. Not just of the same order of magnitude, in a large portion of the ocean, it is in fact much greater than what the diffusive term is. So what this means is that if you want to account or if you want to parameterize the effects of eddies to the first order, you don't just need to parameterize them as diffusive processes, you also need to account for this sort of deposition somehow or the other in your models. And that's the big take-home message from this talk. So really, conclusions, deposition compared to flux or transport is much more relevant for local tracer tendencies, and it allows you to directly compare the impacts of diffusion as well as current advection. Across the majority of the ocean, diffusion does not affect tendencies. So the idea being that the diffusive flux into a grid point is the same as the diffusive flux out. However, near the western boundary currents and the ACC, these values are high because you have really sharp gradients, and that is where your diffusion tends to concentrate tracers. Coherent advection plays a really important role in transporting heat and salts from areas where they originate to where they dissipate. And how would you go about parameterizing? This is something, like I said at the beginning of my talk, I have no idea about. And finally, I will leave you with this beautiful simulation that was conducted by Jonathan Boula in France. This is a Gulf Stream meander. There are pinch-off rings, swarm core rings that have already formed. And what he's going to do is he's going to deposit a lot of Lagrangian particles on the western sort of boundary of this simulation domain. And as these particles get advected by the flow field, you're going to see in a minute that as they come into, or as this eddy interacts with them, it is going to suck in some of this water mass. You're going to observe stirring, as I said before, like the eddy is going to deposit water mass from here to here. But some of these particles get trapped inside the eddy, and essentially are going to get translated along with the eddy as it is going to drift westward. So really, this beautiful figure shows that both of these processes matter for most mesoscale eddies in the ocean. Thank you.
So let's take a few questions from the students first. Anyone who is working in the field of physical oceanography or most possibly Antarctic circumpolar current, Gulf Stream.
How the Coherent eddies
I would suspect, first of all, I don't know. The typical way in which this was something that I was discussing with somebody at IIT Madras just a few days ago, because he was conducting simulations of what happens inside these coherent eddies. And I asked him, how exactly do you initialize an eddy? Like, what do you do? Or how exactly do you prescribe a flow field such that there is a Lagrangian eddy that forms? And what he said was that the formation and the diagnoses of these eddies is the same. What you're going to do is you're going to say that there's a flow field. You're going to advect particles in it. And then wherever these particles tend to congregate is what you call a Lagrangian eddy. I imagine that because Eulerian and Lagrangian eddies are correlated, like typically Lagrangian eddies tend to occur in the cores of Eulerian eddies. The idea is, or I suspect that one of the terms in the vorticity equation that I described in the first few slides. So just via forming these eddies in general, these sort of vorticity structures, you're going to have some regions that are going to concentrate particles, and that's essentially a Lagrangian eddy. But I cannot give you a much more interesting dynamical reason than that. Sorry. Arderian eddies can go all the way down to the sea bottom. Like people, like those are typically diatropic eddies. So if you have a seawater column depth of 2,000 meters, you can have some eddies that go all the way down there. Typically, eddies that form near the ACC tend to be more diatropic. So they are going to extend much deeper than other eddies. Majority of eddies across the ocean, I want to say, so Zia conducted a study of Lagrangian eddies as well in 2023, I want to say. But they said that it was approximately 500 meters or so that these coherency extends down to. You cannot see the depth extent of eddies from satellite altimetry. You will have to use a model for that. And models, of course, can be unreliable. But what you can do, and what Liu and Abernathy did, was that they used the surface expression of geostrophic velocities and then said that they say nothing about the depth extent of these eddies at all. All they say is that at the surface, these are the coherent structures that form, and then you can make assumptions about their depth extent, however you see fit. In our case, we assume these eddies are uniform up to a depth of 500 meters for our analysis, which is wrong, but works the first order of magnitude. And you can't say more than that without a high resolution model or without actually going there and measuring the flow field.
One is about the radiant diffusion,
Yeah.
diffusivity coefficient we should talk. So the temperature change basically went from negative to positive in the Pacific.
Oh, sorry. In the final few pages, Roshan?
No, at the starting when you have shown the paper.
Oh, yeah.
We have tuned the ARAD.
Yes, yeah. Yes. Go on, please. I'll sort
Do
that.
you think so the value which was changed from 400 to 2400 is this one? Yeah, exactly this one. So do you think the models are getting the coefficient this much wrong by this is changed by 6 times?
I don't think the models are this wrong. And the most modern climate models tend to use not just they typically tend to use much more constrained diffusivities than this sort of thing. This was a much larger model run. So what they did was that they had 1,500 years of a model run with a constant diffusivity, which was the same across all of these. And then they changed the diffusivity and then ran for an additional 500 years and then saw how the patterns changed. So this is essentially a tendency after year 1,500 of the model run. Current generation models, I would say, do not get the diffusivity this wrong because we have much more constrained observations of eddy diffusivities now. For instance, like Fjord showed, like the plot that I was showing for the Natre region showed a bunch of like Sylvia's estimates, our estimates, and Fjord's estimates. There's other global estimates of diffusivity as well. And we think that these estimates are are reasonably accurate to what you would expect them to what you would expect to see in the ocean. Another thing is that what this model is doing is that it is taking a constant value of this across the ocean, which is obviously not true. It's going to be much higher in the Gulf Stream than elsewhere. But essentially, the idea behind this work was to say that constraining this is important, and you need accurate values of diffusivity to see what your model is doing, because a large part of your model uncertainty can come from what parameters you're choosing. That was the. And sorry, one more thing. The point of this work was to identify where in the ocean this cooling and heating would occur if you were to tweak your parameters. So the idea behind increased cooling or warming in the north equatorial Pacific, I think, is that if you have a very low value of diffusivity, you're not diffusing warm water to the poleward as much as you are in the real ocean, because eddy fluxes and eddy diffusivity is one of the dominant terms in meridional heat transport. Whereas if there's like this critical sort of value where if you cross that diffusivity threshold, your mean advection is going to get dominated by the eddy flow, and then you're going to observe warming. I think that was one of the conclusions of this work.
Okay. See, at least you're saying that see that
some of them, yeah. Yeah. There's a lot of studies. Dong and Changming Dong and Jim McWilliams did this sort of coherent advective transport estimate of water as well. We think they got quite a few things wrong, but anyways, they used Argo profiles inside Eulerian eddies and then essentially tracked an Eulerian eddy all the way to where it ended and then made assumptions about transport off of that. One of the problems with that is that Eulerian eddies are not coherent. So you're going to vastly overestimate your magnitude of transport because of that. But you can observe these large salinity and temperature anomalies associated with these eddies in Argo profiles. Because eddies essentially, you're going to have associated upwelling with cyclonic eddies and downwelling with anticyclonic eddies. You're going to displace isopycnals from what the main background state of these isopycnals is. And then if you just draw a potential density profile, you can see that difference in your profiles. I suspect that it is actually, well, productivity is a tricky thing. For most of the last few decades, what we have sort of limited ourselves to is the idea that if you have upwelling associated with cyclones, you're going to bring nutrients up to the euphoric zone, and then you're going to boost productivity. And if you have an anticyclone, you're downwelling, and essentially you're depressing water, already nutrient-depleted water down below the euphoric zone, so you are going to decrease productivity. Current understandings, and so what you can do with, for instance, cyclones is that you can have a patch of productivity inside cyclones, and then as that cyclone drifts with it, that patch of productivity or that patch of chlorophyll, phytoplankton, whatever you want to call it, is going to drift along with the cyclone, essentially depositing oxygen or organic matter to where that cyclone dissipates. So that's one of the ways in which you can observe the effect of this sort of transport on biogeochemical stuff. More recently, the idea has grown that it is really eddy edge effects that drive most of this productivity, that the upwelling and downwelling and associated boost is really not that important compared to what happens at the edges. And the reason why that's important is because the edges are sub-mesoscale. They're much more constrained in the horizontal and much, what that implies is that the vertical velocities at the edges are much larger. So you're really upwelling a lot more water at the edges than you are at the center is the current paradigm. So it's a long-winded way of saying that eddies affect productivity quite a bit in interesting ways, both at the core and at the edge. And this sort of coherent transport can drag productivity or chlorophyll or oxygen along with the eddy as it propagates. Shelja Gangrare, who is at Brown right now, she did a lot of work with the S-mode field campaign off of the California coast on some mesoscales and productivity and coherent transport.
Questions?
And what is the difference between eddies and the rings? How can you difference?
Good question. I think rings are eddies, so to speak. Well, typically rings are used in the context of Gauss stream rings. I could be wrong here. I've not done much research in sort of distinctions or into rings. But I think the idea behind a Gulf Stream rings, a warm core ring or a cold core ring, is that the Gulf Stream water sort of wraps around the background water, and then you form this coherent ring structure. That is an eddy. It's just that the properties of the water inside the eddy are very different compared to the water outside the eddy, which is why they're typically called rings rather than eddies. For most of the ocean, the water properties are going to be homogeneous across the eddy because the eddy forms essentially there's not a large gradient of water mass in the region of the eddy formation, but there is for the Gulf Stream. So if you have a Gulf Stream meandering and then you're going to form a cyclone, a cold core cyclone because of that, you're essentially having a filament of warm water that is wrapping around a cold core in the north, and that's a cold core ring, so to speak. But I think that's the fundamental difference, but I could be wrong here.
Yeah, it's very nice talk. Actually, I'm not from the oceanography field, but I'm quite interested to know what is like what differentiates out between FTLE tracking of the particle, LCS, and LAVD, as well as Okuwe's waste parameter. So, like, if you for particle trajectory, you use FTLE, so you need like backward as well as forward integrations and then computing and then getting the inflection point. So, based on in that inflection point, you get your LAVD, and then that instead of that gives computation. Why not we prefer for all the two parameter? Why is there any restriction for that?
I don't know. You should probably read the Lou and Abernathy paper to see why they did NVD stuff compared to
even Heller's papers.
Yeah.
They from the ETAs, they do the same thing. First they compute FTLE, LCS, and then go for the LAVD.
Yeah.
But they directly don't go for LAVD. I think.
Yeah, they do not. I don't know why. I have not done much research into how exactly you define coherency. Yeah, I don't know.
Okay, one more thing is that could you count the number of eddies?
Yeah, we did that. I should have put that plot here. Actually, maybe I did. I don't know. It's in the paper, at least in the draft paper right now.
So can you throw some light on it? How did you do? You get the inflection point and then count that?
No, the idea with the Lou and Abernathy paper is that essentially you are going to compute the LAVD, and what they define as a Lagrangian ring is essentially a closed contour of the LAVD field. So wherever you have a really large, I have that map here actually. This is an LAVD map across the ocean. In the northern hemisphere, this shows 30-day LAVDs. So you're going to see the advection for 30 days and then backward project to find what the LAVD is. And in the southern hemisphere, that's for 90 days. But essentially, you can draw closed contours around around some threshold that you set for what your threshold is. And if you set different threshold, you're going to observe different levels of coherency. In one of the slides where I was talking about coherent advection for the first time, I had this map of yellow particles versus red particles versus blue particles, and that refers to different threshold values for your LAVD. So what they observed was that a threshold of, I think, 0.7 was, I think it was 0.7, I don't know. But 0.7 threshold showed that the particles stayed coherent for as long, or they stayed within their within what they thought was a coherent core for quite a while. So that's what they chose for their analysis. And then you can, at each snapshot of your model, or at each you can count how many closed contours there are, and that's your number of eddies.
You count the center of the eddy.
Yes, yeah.
But if the eddies overlap, how do you segregate it?
You're going to say that they merge. I think that's what they said.
Okay. Thank you very much. No.
Nice talk. Very interesting. So you have calculated the eddy diffusivity 500 meters and 1000 meters eddies?
What I showed was for an isopycno, because that is much more, I think, relevant than depth levels. But you can back project isopycnos to depth, and we calculate this for the entire water column from 0 to 2000, because that's the depth of the Argo sampling thing. For instance, for this region in the North Atlantic, our profiles for the diffusivity are using. So you have depth and spatial graded values.
You used also some of the Argo forts in Bay of Bengal.
Yeah.
Do you think, like, how many of those Argo forts you have in Bay of Bengal? generally we have very less.
I had a
reliable is your different.
I had a map showing the locations and times of all Argo floats in Bay of Bengal, Arabian Sea, as well as Eastern Pacific for another seminar, but I don't have that period yet. The idea with this is that across 15 years of the Argo program, you have quite a large sampling of the water column at each location. I think there is definitely more than 10,000 or 15,000 profiles in the Bay of Bengal. The point being that intra-annual effects are expected to not change the diffusivity as much. So if you take away the oscillations and stuff like that, you're not going to see large changes in your diffusivity. So even if you do not have a large number of profiles at a given time, across 15 years, you have enough profiles to be able to characterize what the mixing length is and therefore what the diffusivity is. So you're going to bin all of these profiles into one spatial bin. So in a way, that is a criticism of Sylvia's work in that you are going to be averaging across all of these years. But the estimate is that in the balance, all of the oscillations and stuff kind of average out and you get an average look at the ready diffusivity.
Any difference in depth of these eddies from Bay of Bengal to definitely to Antarctica? So how much of those percentage of eddies do you think they are much shallower and deeper to 2000 meters? And can you consider only about deeper eddies? How about the shallow eddies? They important to change the system.
So shallow eddies are going to be very important for instance, freshwater transport in the Bay of Bengal. Nihar Paul had a paper with Professor Sengupta in 2021, where they talked about how this mesoscale eddy formed at the right off of the coast of, I want to say Odisha, or I'm not sure. And essentially, it was trapping fresh water inside that eddy. It was transported offshore and then it drifted, merged backwards. What it did was that it homogenized the water inside this eddy because of mixing effects inside the eddy and so on. And that was a pretty shallow eddy. I want to say that was a pretty shallow eddy. That sort of... I have not, because the Luan Abernathy Lagrangian eddy dataset does not tell you anything about the depth of the eddy. We have to make assumptions about the average depth, or so essentially the numbers that I say here, the numbers that I'm saying here are largely only accurate up to an order of magnitude. And the aim of this sort of study is to just show that they're important and where they're important. As you can see in the Bay of Bengal, they're not super important, or you can see they're not super important for this sort of larger scale transport because the eddies are not traveling far. So the water properties from at the final location of the eddy and the initial location of the eddy are not super different. So for heat and salt, it does not matter, but I expect for productivity, it matters quite a bit because you're transporting highly productive offshore waters to the offshore open ocean.
Will you use this
I am not going to inform. I mean, this is essentially just a data set of kappas. I'm not going to run a model with these kappas to check what the differences is. That is not what the aim of my thesis is. I'm probably going to use these kappas to say something about what the diffusive flux of oxygen in the Eastern Tropical Pacific is, because that's what I am interested in and what the ONR is interested in, and they're funding all of this. And then we can compare to what previous estimates of diffusive fluxes were and how much they change. That is about the extent of what I'm using this kappa for in my analysis. Probably. I hesitate to call it a bias, but I want to say, yeah. Another important point that I would make is that Sylvia never claimed that these numbers were representative of the length and time scales of current generation climate models. She said that these numbers are accurate if you're considering length scales of about 3 degrees and a temporal resolution of about a month. So if you're running a large, actually not even a month, like a few months. So if you're running a large climate model at those resolutions, you should probably use Sylvia's numbers. But what we want to what we are claiming about our numbers is that these should be accurate to about monthly timescales of timescales of about a month, because the climatology changes at that temporal scale, and at length scales that are eddy permitting. So if your model is roughly a degree or so, which is about the length scale that we're claiming our numbers are accurate at.
Yeah.
Yeah.
So there are a few other approaches where the diffusivity is modified or increased. For example, to take into account the effect of breaking waves. So in that case, some part of your diffusivity is already enhanced. So how does that help in your parameterization? Because you are going to take into account some non-local processes. Whether that development will hinder or that will help your parameterization.
So breaking waves typically do not modify along isopycnal diffusivities, but they do modify diapycnal diffusivities. So essentially, what a breaking wave probably does is it enhances turbulence. And what turbulence does is that it mixes water masses across stratification. So that's typically what we call a diapycnal diffusivity. And our analysis is just along isopycnals. And so I don't think that breaking waves should be impacting this parameterization at all. In existing models, I think the effect of breaking internal waves and where exactly they break is quite important, because they typically use vertical diffusivity parameterizations that are K epsilon or KPP, and what the background diffusivity is depends strongly on where these internal waves are breaking. But for our purposes, I don't think the breaking of waves matters for the transport effects that I'm talking about.
Because it also makes along across the isopycnal.
Yeah, across isopycnals, but I don't think we are talking. Yeah. I don't expect them to matter that much for the profiles, but I don't know.
Questions?
Good question. This is what the person that I was talking to at IIT Madras was also researching or researched and talked about. There is 3D recirculation happening inside these eddies, and they are going to homogenize. I expect that they're going to homogenize water inside the eddy, inside this coherent eddy. Homogenization does not matter for the transport estimates that we have given, because we are integrating across depth. So even if you're homogenizing the water inside the eddy, you are still going to have the same tracer content. So the transport estimates are not modified, but what is modified is at which depth and isopycnal level that transport occurs. So whatever vertical circulation, whatever vertical flow is happening inside the eddy, what you're going to do is you're going to change the salinity and temperature profiles, and then as the eddy translates, you're going to have different transport estimates at different depth and density levels. But if you integrate, all that effect goes away, and you're essentially just left with net transport. So I think the numbers that I have given are independent of what's happening inside the eddy vertically. But if you were to decompose this into what is happening at different density or depth levels, you would observe a change. It does change. Not by they do decay with depth, and the decay is more significant at depth than mid depth levels, I want to say. But yeah, that is another sort of caveat or flaw to this sort of simplistic analysis. And that comes with having no idea of what the depth of these eddies is doing. And you're right that it does change. And the question of what happens to eddies as they're propagating, what the evolution of eddies is actually quite an active area of research, I want to say. There's a lot of groups in France, Jan Barabino's group, Basile Gallet's group, are working quite a bit on modeling eddies and what happens as the eddy propagates. There's a lot of active work, unfinished work on how exactly does an eddy die in the first place, like what exactly happens to make it dissipate. We were having this discussion with Professor Sengupta and Professor Mahadevan from Puri as well. And there's a lot of unanswered questions. So we are making approximations that we think are appropriate that people have made in literature, but we know that these approximations are wrong. How wrong they are, I don't know.
If any more questions, you can take offline with Parth. Parth is there throughout the day today at IITM. So on that note, let's thank Parth again for his wonderful talk. Thank you, Parth. Thank you everyone for joining. Thanks.